and welcome to Physics 2, Lab 2, Charge Tape Revisited. Introduction. The purpose of this lab was to observe the polarization of two insulators, create a computational model of these insulators experiencing the gravitational and electric forces, showcase the computational model under these given assumptions, and understand the effect polarization can have on the insulated materials. The physics principles utilized in this lab were electric polarization, which is the separation of positive and negative charges in a material, Coulomb's law, which calculates the force between two charged particles at rest, Newton's third law, which states for every action there's an equal and opposite reaction, and the equations, which is the force of gravity equation, the electric field equation, the electric force equation, the equation for the electric force of a rod, and the principle of superposition. Here's a preview of my results and the models. The observational model was discussed more thoroughly in Lab 1, but a quick review was it was an experimental analysis lab. It was recorded through photos and qualitative analysis, with the only quantitative measurements being documented were the length and mass of the tape. And then the computational model for this Lab 2 was made in GlowScript code, assumed the length of tape to be polarized and a rod, and then it predicted the forces applied to the charges of the tape as it floated midair. So the experiment, once again, Lab 1, it was recorded, it was photographed. Computations, we have the tape length, which is 0.2 meters, distance between tapes, the mass of the tape, net charge tape, acceleration due to gravity. Computational model, once again, created in GlowScript code to show the forces at equilibrium as the charged tapes repelled each other. So let's get into that. Boom, the code. We have our physical constants. Over here, we have the electric constant K, acceleration due to gravity, mass of the tape, net charge of the tape. Down here, we have our function, which describes the electric field equation and how you get those vectors for each dq when you go through the rod. Over here, it's just the initialization of each rod of tape, of the two tapes in our computational model. And down here we get into the nitty-gritty where it's going through each infinitesimally small dq and calculating the force electric for each one, and then it adds them all up to make one big force electric vector, which will oppose the force of gravity vector, which can be seen here. We have each individual, this is for 30 charges, I believe, and of course it gets more accurate the more charges you calculate. We have 30 different force electric vectors for 30 different dqs. They all add up together, their x components cancel through superposition, and we get one big force electric vector which opposes the force of gravity. So let's talk about this. Why are the calculated charges in Lab 1 and Lab 2 different, with Lab 1's calculated charge being 1.2 times 10 to the 8th coulombs, while Lab 2's experimental model, it was found to be 2 times 10 to the 8th coulombs. That's a 1.66 times difference. Well, the difference is mainly due to the parameters of each computational model, with Lab 2's resultant charge ending up to be more accurate than Lab 1's, because each of these models still assume the same sources of error from Lab 1, that either being the humidity impacting the charge or the material of the tape impacting the charge. But Lab 2 discusses them as a rod, which is more accurate to an actual tape-like shape and more accurate to that separation of charge throughout the tape, while in Lab 1 it was just a point particle impacting a point particle. So that's really the greatest source of difference between these two. Everything else stays the same, the system and surroundings stays the same. It's just how we identify our model. So in conclusion, this lab showcased the effect and importance of electric polarization and how the shape of structures and objects can influence the impact electrostatic forces have on them. Thank you for watching.